Very important topic, both from gate point of view and from the concept point of view for signals and systems. Okay, what is Fourier transform? We have seen Fourier series for continuous time periodic signals. Okay, now if generally the signals which exist in nature, they are continuous time and non-periodic. Okay, so definitely they cannot have Fourier series for that. For those signals we are having Fourier transform, because anyway for any signal there are always a frequency domain representation. So this is for continuous time non-periodic. It is also called CTFT, continuous time Fourier transform. Okay, how this Fourier transform? See what they I can assume any signal xt which is continuous time non-periodic as a periodic signal with period is infinity. Okay. From this particular basic concept, the analysis equation and the synthesis equation of Fourier transforms are determined. Okay. Now we will directly write the equation for the Fourier transform. Xf equal to minus infinity to infinity xt e to the power minus j 2 pi ft dt. Okay, in terms of omega I can write omega t dt. Similarly, this is a analysis equation because from the given signal xt I am deriving xf. Now synthesis equation, xt is equal to minus infinity to infinity xf e to the power j 2 pi ft df, or in terms of omega it is 1 upon 2 pi minus infinity to infinity x of omega e to the power j omega t d omega. 1 upon 2 pi does not have any meaning as such, but mathematically it comes into the picture. That's why we are writing it. Otherwise, there is no importance of writing 1 upon 2 pi as such. Okay. Now this is a Fourier transform synthesis and analysis equation. Okay. Now, but we should also understand this Fourier transform may not exist for certain things and it may exist for certain things. So, to understand what are the conditions under which the Fourier transform will exist, okay, these conditions are called Dirichlet's conditions. Okay. Dirichlet conditions. Dirichlet's conditions are the sufficient conditions. They are not necessary conditions. Okay. There are certain signals which does not satisfy these Dirichlet's conditions but still possess Fourier transform. Okay, we will see that. But there are three conditions known as Dirichlet's conditions. If these conditions are satisfied, that means Fourier transform will exist. The first one is the signal xt should have finite number of finite discontinuities. Okay. Signal xt must have finite number of finite discontinuities. Second one is signal xt should have finite number of maximas and minimas. Minima. Okay, this is second condition. Third condition is the signal xt must be absolutely integrable. Minus infinity to infinity mod xt dt be lesser than infinity. Now, these three conditions a signal must satisfy in order to have a Fourier transform. But write note. First, step function xt equal to ut. This function does not satisfy Dirichlet's condition. But still have Fourier transform. Okay? Because if we look for the absolute integrability, this is equal to infinity. It is not less than infinity, but it is infinity. Thus, not absolutely summable. Integrable. Sorry, it is continuous sign. Second, xt equal to sine omega t. This also does not satisfy the Dirichlet condition. Why? Infinite number of maxima and minima. But this also possesses Fourier transform. Okay. Then we can make a note of third point. Dirichlet conditions are sufficient condition but not necessary. Okay. So these are the conditions. Fourth point that is different other than the Dirichlet condition. Fourier transform is a special case of Laplace transform. Okay. In Laplace transform we have S which is equal to sigma plus j omega t. If sigma equal to 0, S will become j omega t, which is called Fourier transform. Okay. So these are the 4 points should be remembered. Okay. Now we will proceed further. Next is energy density spectrum. Okay. Energy, this is a continuous time non-periodic signal. So since it is a non-periodic signal, it will possess energy, not power. So we will have energy density spectrum. Energy in this case is minus infinity to infinity xt square dt. This is also equal to minus infinity to infinity xf square df. Okay, this is called Parseval's relation for non-periodic finite energy signals. Okay. Next, looking at the spectrum of the Fourier transform xf or x of omega. Xf magnitude e to the power j phase of xf. Magnitude spectrum is even, while phase spectrum, this is an even function, while phase spectrum is not an even function. It is a odd function. Okay. Energy density spectrum is also even. Phase information completely lost in energy density spectrum. Okay. Now, if energy density spectrum is given, then can we identify the signal xt? Just listen, just think over this. If energy density spectrum of a signal is given, then if question comes to find the signal xt, if energy density spectrum is given, then can we find the signal xt? The answer is no, because to know the signal completely, we should also know the phase. But the phase information is completely lost in energy density spectrum. So that's why write a note. To completely identify signal xt, we should know magnitude spectrum as well as phase spectrum. Then only we can get the complete information for the signal xt. Okay. Now we will see the Fourier transform for a very special signal, that is a rectangular pulse. Rectangular pulse is defined like this. Okay. If I plot over this, it will be something like minus tau by 2 to tau by 2 a and t. This is a rectangular pulse. For this, I have to find the Fourier transform. Before finding the Fourier transform, I should verify that xt must satisfy all the Dirichlet's conditions. Okay. If it is satisfied, definitely it will have a Fourier transform. So, xt must satisfy all the Dirichlet's conditions. First one. The first Dirichlet condition is finite number of finite discontinuities. So there are only two discontinuities and these two are finite. Okay. First condition is satisfied. Finite number of maximas and minimas. So that condition is also satisfied. Third one is the absolute integrability. This definitely it is absolutely integrable. So minus tau by 2 to tau by 2 a dt. It gives me a tau. So it is a finite. So third condition of the Dirichlet condition is also satisfied. So now definitely it will possess a Fourier transform. So writing the analysis equation of Fourier transform, xt e to the power minus j 2 pi ft dt. Okay. So my limits of integration will be from minus tau by 2 to tau by 2 a dot e to the power minus j 2 pi ft dt. Okay. On solving this integral, I will get a tau dot sine pi f tau upon pi f tau. This particular thing is called sinc function. Definitely this sinc function will exist in all types of signal, whether it is a continuous type periodic, continuous type non-periodic, or discrete time periodic or discrete time non-periodic. Okay. Accordingly, the sinc function will become continuous or discrete if it is a periodic or non-periodic respectively. Okay. So this is a Fourier transform for rectangular pulse. Okay. Plot of sinc function. From the given function, magnitude at the top is a tau. This is that. This is my frequency axis. This is magnitude. This is f equal to 0. These points are 1 by tau, 2 by tau, minus 1 by tau, minus 2 by tau. Okay. Now depending on the pulse width, this sinc function will compress or expand. Okay. And the magnitude of this also depends on the pulse width. So we will see the various cases under which the effect of pulse width is seen in the sinc function. Okay. Write a note. The first one. See, it is a non-periodic signal, so there is no concept of periodicity in this. So there is no T in this, no capital T in this. We will have only tau, that is a pulse width. So we will change only the pulse width. If pulse width reduces, that is tau decreases. Then what will happen if tau decreases? Then a tau will also decrease. A tau decreases, that means magnitude decreases. But 1 by tau will increase. This cause is spread in frequency domain. That means now the plot will look something like this. Okay, it is spreaded. Earlier it was much compressed. So the effect of decreasing pulse width will cause these two things in the sinc function. The second one. If pulse width increases, now whole things will get reversed. If pulse width increases, that is tau increases, that will cause a tau to increase, then magnitude will increase. Okay. The increase in magnitude, again 1 by tau will decrease. This cause a compression in frequency domain. Now how this compression will look, we'll see. Now if we draw the frequency domain in the second type, when pulse width increases, it will be something like this. Okay. Compression takes place. Okay, so these are the two different things which happens depending on the pulse width increase and decrease. Here the only variable is pulse width. Magnitude anyway is a variable, but the magnitude variable will not have any effect on the frequency domain. Neither it will compress nor it will expand, but only magnitude at f equal to 0 will increase. The third point in this we have observed is Fourier transform for a non-periodic continuous signal is continuous and non-periodic. Fourier transform of non-periodic continuous time signal is continuous and non-periodic. Okay, so this is a general basic about the Fourier transform. Okay, we will see also some properties later in the upcoming topics regarding the Fourier transform. Properties for the frequency domain, either for Fourier series or for Fourier transform, or either for CTFS or DTFS or DTFT or CTFT, the properties will more or less remain same. Okay,